All right. We just involved ourselves in actually experimental probability once again. Last week it was flipping. No, we're actually doing one die there. Now it's two die. So we want to see if we got a 10. Here's your trials. So we actually did it and we recorded. So this is actually experimental probability. I'm going to do the probability for us up on the board. You pay attention. Okay? Stay with me, Ramirez. Put off too. All right. Ramirez, since you're giggling, what you guys get? How many 10s? Out of 50? Magana? Out of 50. Sevilla? Ekasan? Marin? Oh, yeah, my bad. Hernandez? You okay? Someone give me a hug there. Miss Ramirez. Check that out. It's pretty trippy. And Sakaitos?
Yeah, you don't even know me. I swear to God, like.
Don't swear to God. But go ahead.
I swear on my grandma's grave. Every single one I was getting, I was getting 10 constantly.
That's crazy. That's crazy.
Weird stuff like, well, for example, I was getting like catch, spin around and rely on 10 more. Maybe I don't know. But did it this time? A lot of the times it was.
All right. Thank you. Thank you. Okay. So here we go. Thank you for that, Gallegos. All right. Let me get my calculator. So let me add up all the 10s. 8 plus 5 plus 7 plus 5 and 5 plus 4 plus 17. So the experimental probability of rolling a 10, look at the way I'm writing it out, is 51 out of 100, 200, 350, out of 350. Okay? So let me do that. Let me do that calculation now. That's as a fraction. It's actually reduced at this point. 51 over 350, there's no common factors. So that's actually a reduced fraction as we have it. Let me do it as a decimal now. 51 divided by 350 on my calc. As a decimal, it's 0.015, which is, as a percent, 15%. So when you toss two die, it's a 15% chance you'll get a 10. Now, let's do experimental now, or theoretical probability. Let me put that in red. Theoretical, I have the sample space up here that I just passed out to you. Here's a sample space of rolling two die. Let me circle all the outcomes that have a 10 in it. Here, actually that's 9, huh? We got 10 here, and we got a 10 here. Any others there? That's it, huh? There's only 3 possibilities out of what? How many total outcomes are in the sample space? Let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So out of 36 possibilities, watch my experimental now. Let me talk, gentlemen, please. Excuse me. So theoretical probability, I'm going to put in red now. TH probability of, put B, TH, theoretical probability of getting a 10 is going to be 3 out of my sample space. So that's going to be 3 out of 36. Let me reduce that. 3 goes in 3 once, 3 goes into 36. Let's see, 36 divided by 3, I think is 12. Yep, 12. So there's my reduced fraction. 1/12 as opposed to, I couldn't reduce that, but let's get the decimal. Let's see how close, let's see how close theoretical got to our experimental. Check this out. 1 divided by 12 as a decimal, 0.08. Okay, 0.08 as a decimal, which as a percent is 8%. So look at how far away experimental versus theoretical. Experimental versus theoretical. What kind of messed it up, I shouldn't say messed it up, was the 17. There may be a flaw in Gallegos' the way he was tossing this and that, I'm not sure. But, let me answer this phone here. All right. So what's the big idea? It was about a week and a half ago. How does it happen where the experimental gets closer and closer to theoretical? Do you guys remember when we did that? The first toss last week? What has to happen in order for the theoretical in red and the experimental to get closer and closer to each other? Do you guys remember what happened? Say again? Right. In other words, more trials. Exactly. The more trials, the higher this gets. If we were to do this all day as a class, our experimental would get closer and closer to 8%. That's the key about probability. In the long run, it's very predictable. We can tell the future in the long run. In other words, the more trials. In the short run, you can't really predict what you're going to get every time you toss those two dice. But in the long run, you can say, you know what, after 1,000 dice tossed, you're going to get a 10, 8% of the time. So it's like a predicting power with probability. Okay, I'm going to come around and collect the die and pass out your next note guide. We'll only take notes for about 10 minutes. Easy notes today. Would you? I appreciate that, Magana. Magana's going to come around and collect the die. Go to put your desk back. 10 minutes of notes. 10 minutes. Put this in your binder.
Can I go to the baño?
Not yet. You're next up. Magana's collecting the die. So you have the note-taking with vocabulary. Let's go ahead and define the first word, independent events. Independent events. So here's what you're going to write on independent events. Events that do not affect the probability of each other occurring. A little typo there, not of each other, just of each other occurring. Events that do not affect the probability of each other occurring. Events that do not affect the probability of each other occurring. Events that do not affect the probability of each other occurring. Flipping a coin and rolling a dice would be an example. So if I flip a coin and roll a die, well, I'll wait till you guys are done writing. Excuse me. When I use the word affect in this way, Murillo, let me talk, please. When I use the word affect in this way with an A instead of an E, that means to influence. Influence. If you forget what that means, maybe in parentheses, influence. Events that do not influence the probability of each other occurring. So if I said, if you flipped a coin and roll a die, I said, what's the probability of you getting a 5? Actually, we're flipping the coin first. Let's flip it. So what's the probability of you having a coin in one hand and a die in the other and getting a heads and then getting a 5? Now, before we even calculate it, what you get on this coin does not affect how the dice lands. In other words, the dice does not care if what you did was land heads or tails. And vice versa, the coin doesn't care what the dice does, and the dice doesn't care what the coin does. We call these independent events. They're independent of each other. This does not influence the coin does not influence the die. We call them independent. And here's how we calculate it. If it's independent event, we take each event, the probability of the heads, and we multiply it by the probability of the other one. In this case, the probability of a 5. If they're independent. Think of what you just did with 2 die. The first die that you rolled and the second die you rolled did not care about each other. That would be a case of independent events, what we just did. The first die didn't care if the second one was a 5 or 4 or 3, 2, 1, doesn't matter. They didn't care. Those independent events. So let's do this really quick. The probability of a heads and a 5, I'm going to take each individual probability and multiply those puppies. Watch what happens. What would be the probability of getting a head as a fraction? 1 favorable out of 2 possible, huh? There it is, 1 out of 2. Look at now, bring down the times. Probability of getting a 5. 1 out of 6 on a die. Look at this. Let's multiply these puppies. Fraction times a fraction, Ramirez. Stay with me. 1/2 times 1/6. Let's see, numerator times numerator is 1. Denominator times denominator, 12. There's your probability. 1 out of 12 times. You flipping a coin and getting a head and then rolling a 5 on a die will happen 1 out of every 12 times on average. It'll typically happen 1 out of every 12 times. So this is how we figure out independent events. Something and then something else, if they don't care for each other. But what if they do influence each other? For instance, dependent events. Let's write this one down. This is the only two words for today. Dependent events. Events that do affect the probability of the other. Example. From a deck of cards, getting an ace without replacing and then another one. Yeah. There's dependent events. Events that do affect the probability of the other. Think of a deck of cards. You're at a casino. You want to get 2 aces. You know if you get 2 aces, you're going to win the bet. What would be the probability of getting 2 aces from that deck of cards? We're about to find out. But before we find out, I want you to see how the first probability influences the second. Let's think about why, but I'll let you finish writing this down. Go ahead. You seem confident. Everybody. Here we go. All right. How does the first probability of me getting an ace from that casino the casino dealer influence the second ace? Does anybody see how that happens? Murillo, what do you think? Hold up. Go ahead. Right. So your sample space is reduced now. Say that one more time, Murillo. Or Moran. No, Marin. Third time's the charm. The second time the dealer gives me a card, not only has the sample space been reduced from 52 cards to 51, but the amount of aces has gone from 4 to 3. Notice that. So Write this down with me underneath this. The probability of getting an ace and another ace. I'll put a sub 1 and a sub 2. The first ace and the second ace. Is going to equal, watch this, the probability of getting the ace, the first one, times the probability of getting the second ace, given that you got the first ace. So I want you to put a little bar and put, this means given that, or assuming that. It's a little different than what we did up here. It's just probability of the heads times the probability of 5. But here now, it's the probability of the second ace given that you actually got the first ace. Or assuming that you got the first ace. So when you see this long bar like this, all that means is given that. It looks fancier than it actually is. There's no mystery to it. It just means given that. So it's going to be the probability of getting an ace times the probability of getting the second ace given that you got the first ace. Watch how I do this. Watch. Here we go. What would be the probability of getting one ace? How many aces are there?
4.
4. There's a spades, there's a jack, or there's a spades, there's a clubs, there's a hearts, and a diamond of aces. There's 4 of them. So 4 out of total cards is 52. Let me follow this. Times. Here we go. The probability of getting the second ace, assuming they got the first one. Now, I don't have 52 cards anymore. I have 51 cards. Notice how it depends. See, this depends on that. We call them dependent events. This is influenced by the first ace I got. And now there's not 4 aces, there's only 3 aces. There we are. So this is a fraction times a fraction now. 4 out of 52 times 3 out of 51. Let me go and calculate that. 4 times 3 is 12. 52 times 51. Let me get my calculator. Let's see. 52 times 51. 2652. It'll happen 12 times out of 2,652 tries on average. So it's very unlikely. Let me get the decimal really quick. 12 divided by 2652. I got this. Watch this. 0.00452 and so on. So it doesn't even round off to 1%, because look at the 0. This is the hundreds place. I look to the right of it. It's not 5 or bigger, so it's not even 1% chance. Let's round the nearest thousands then. This is a thousands place. I look to the right of it. This is 5 or bigger, so this will be 0.005. That means tens, hundreds, thousands. That means it happens 5 times out of every 1,000 tries, getting 2 aces in a row. So 5 times out of every 1,000 tries, or 12 times out of every 2,652 tries. Means the same thing. It's a different way of saying the same thing. So it's very unlikely. So whenever you get a nasty decimal like this where you can't even round out to the nearest hundredths, because look at the thousands place is not even 5 or bigger, we're talking about a fraction that's so small you can't even, it's not even out of 100. It's out of 1,000 now. Smaller probability. I'm going to continue with this tomorrow just a little bit before I give you quiz 2. Tomorrow, you can make up quiz 1 if you never did it, or if you want to just do it over because your grade will just like vomit and you couldn't stand looking at it, you can take it over for a brand new grade. Right now, you work on assignment 1, 2, or 3 from your Google Classroom. Get your Chromebook. Assignment 3 is right here by my Raider helmet. Go Raiders. It's right here, assignment 3. Use your time wisely so I can stamp you. Let's do it.